Hi, my name is Olivier Martin. I'm a postdoc at Stony Brook University, and today I'm going to tell you about the degree of irrationality of abelian surfaces. In particular, we're going to see how we can use results about rational equivalence of zero cycles in order to deduce some facts in birational geometry. So let X be a projective variety over the complex numbers. We're going to consider the following birational invariant: the degree of irrationality of X, so it's the following. It's denoted ir of x, and it is the minimum of the degree of f, where f ranges over all dominant rational map from f to a projective space of the same dimension. Right, so in particular, this measures the failure of x to be rational. So x is rational if and only if the degree of irrationality of x is equal to 1. So this, in the case of curves, has a much more classical name. It's been studied for quite a while. So if x is equal c as a curve, then the degree of irrationality of c is known as the gonality of c. So as the title suggests, we're going to be concerned mostly with the case of abelian varieties and abelian surfaces in particular. So the first result in this direction is a theorem of Alzati and Pirola from 1992. So what they prove is that if A is an abelian surface, then the degree of irrationality of A, well, if A is an abelian variety, then the degree of irrationality of A is at least the dimension of A plus 1. So for instance, if I have an elliptic curve and the degree of irrationality is at least 2, this is actually an equality for elliptic curves because, of course, elliptic curves are double covers of the projective line. So in particular, if we're looking at the case of abelian surfaces, we see that abelian surfaces have a degree of irrationality at least 3. So in particular, they're not just not rational, they're also not double, birationally they're not double covers of the plane. So this term was shown to be sharp in the case of abelian surfaces. So this is by Tokunaga and Yoshihara. It's not known if it's sharp for higher dimensional abelian varieties. So it's 1995. So what Tokunaga and Yoshihara show is that, as I said, this is sharp for abelian surfaces. So they exhibit abelian surfaces which have the degree of irrationality 3, and in particular their construction is the following. So they show that if you have an abelian surface that contains a smooth genus 3 curve, then this abelian surface does admit a degree 3 dominant rational map to the projective plane. So the construction is the following. My smooth genus 3 curve has to move in a pencil of genus 3 curves, and the general member of this pencil cannot be hyperelliptic. So this is something that you have to show, but the general member cannot be hyperelliptic, so it has to be uniquely trigonal. So using all of these trigonal linear systems, we get a rational map from the abelian surface to a P1 bundle over P1, which is itself a rational surface. And this rational map has degree is dominant, and it has degree 3. So this is the construction of Tokunaga and Yoshihara. So just a year later, in 1996, Yoshihara asked some questions about the behavior of this degree of irrationality. So the first question is, are there abelian surfaces with degree of irrationality greater or equal to 4? And the second question is the degree of irrationality of an abelian surface an isogeny invariant? So there's no reason to believe that it will be an isogeny invariant, but it's it's a valid question. But there's nothing that suggests that it would be an isogeny invariant. Of course, if you have a dominant rational map to projective space, you can compose this rational map with an isogeny, but you're going to get a dominant rational map to projective space that has a much larger degree. So this is not, it's not at all obvious to talk about whether the degree of irrationality is isogeny invariant or not. So while there was little progress in Yoshihara's questions, there was progress in the opposite direction. So in particular, there was a conjecture of Bastianelli, Depoy, Ein, Lazarsfeld, and Ullery that was made around 2017. And so what they conjecture is that the degree of irrationality of a very general 1D polarized abelian surface goes to infinity with the degree of the polarization. So basically, there are abelian varieties with arbitrarily large degree of irrationality, and actually, if you look at there are very general abelian varieties with arbitrarily large degree of irrationality. So this conjecture was disproved by Chen, which is a student of Lazarsfeld, but it actually turns out that when it was formulated, it had already been disproved somewhere in the literature. So buried in a result of Kuhn was the following construction, which you can do to obtain a dominant rational map from an abelian surface to P2. So the construction of this is the following. So you can start with an abelian surface. You can quotient by plus or minus 1. So you get down to something which is birational to a Kummer surface. So the result of Kuhn that I'm alluding to, so Kuhn showed that every Kummer surface is the K3 cover of an Enrique surface. So what this means is that there's a non-symplectic involution acting on a Kummer surface, such that the quotient is an Enrique surface. So from this variety A quotiented by plus or minus, which is birational to my Kummer, I could quotient by this non-symplectic rational map, this non-symplectic involution on the Kummer surface, and I can get a rational map to an Enrique surface. But it's a classical fact that an Enrique surface is birational to a double cover of the projective plane. So I actually get a double cover of the projective plane over here. So I have a rational map here which is 2 to 1. This rational map is 2 to 1, and this rational map is also 2 to 1. And so composing all three of these dominant rational maps, I'm getting an 8 to 1 rational map. So this already shows that the degree of irrationality, and this the result of Kuhn, so the result of Kuhn is this thing here, the fact that we have this non-symplectic involution. So the result of Kuhn is from the 90s, and so already this showed that the degree of irrationality of any abelian surface is less than or equal to 8. So the theorem of Chen is a bit stronger, and we're going to need it in its full form. So this is Nathan Chen. It's Tony Brook. So he shows that if A is a very general abelian variety, so what he needs actually is just that the narrow-separated group is isomorphic to Z. So if A is a very general abelian variety, abelian surface, then the degree of irrationality of A is less than or equal to 4. So he explicitly constructs a degree 4 rational map to P2. So this was improved upon by Chen and Stapleton. So what they managed to do is to remove this very general assumption. So the offshoot of this situation is we have this invariant, which we call the degree of irrationality. And for abelian surfaces, we know that this degree of irrationality is either equal to 3 or it's equal to 4. So we had plenty of examples where it was equal to 3, but we did not have a single example where the degree of irrationality was equal to 4. Even though it was widely conjectured, in particular Chen made this conjecture in his paper, that the degree of irrationality of a very general abelian surface should be 4 for most polarization, for most choice of a polarization type. So the result that I want to present today is the proof of this fact that the degree of irrationality is typically 4. So the theorem is the following. So if A is an abelian surface with the degree of irrationality 3, then the image of the following pairing. So I have a pairing that goes from sim2 of the narrow severity group of A. So this is the image of divisor classes inside cohomology. So I can take the cut product of such divisor classes, and this is going to land me into Z. So the image of this intersection pairing on the narrow severity group contains 12. So this is a very restrictive condition for abelian surfaces. So actually, like the wide majority of abelian surfaces will not satisfy this condition. Of course, if I look at, for instance, product of two elliptic curves, then they certainly satisfy this condition. 12 does lie in the image of the intersection pairing. So, but an upshot of this, so a corollary, So this is a theorem I didn't attribute it, so this is a theorem that I proved in 2019. So the corollary is that a very general 1D polarized abelian surface has degree of irrationality 4 if D does not divide 12. So in particular, this leaves a handful of exceptions that are not covered by this theorem. So we can ask what happens for very general 1-1 polarized, very general 1-2 polarized, very general 1-3 polarized, and very general 1-6 polarized abelian surfaces. The case of very general 1-2 polarized, that is actually resolved by this theorem of Tokunaga and Yoshihara, because in this case the degree of irrationality, we know that it's going to be equal to 3, because a very general 1-2 polarized abelian surface does contain a smooth genus tree curve. So the polarization is going to be given by a smooth genus tree curve. Okay, so let me say a word about the proof. I'm going to explain how we prove this result, and the main ingredient is a theorem of Mumford. So it's the basic theorem about rational equivalence to zero cycle. So what does Mumford's theorem tell us? So I take S, a smooth projective surface, and I consider omega an element in so a global holomorphic 2 form on my surface. So for this result to be interesting, I need to have a non-zero global holomorphic 2 form. I'm going to state here the statement without assuming that omega is non-zero, but you're going to see from the statement itself that if omega is equal to 0, I'm not really getting anything interesting. So, and I'm going to get let S subset of S to the K be so this is a subvariety of S to the K, and I'm going to assume that this is contained in a fiber of the following map. I have a map that goes from S to the K to chow 0 of S. This map takes an ordered K tuple of points and sends it just to the effective 0 cycles, which is the effective 0 cycle of degree K, which is represented by this K tuple of point. So saying that my Z is contained in the fiber of this map is the same thing as saying that Z is parametrizing effective 0 cycles of degree K, well, with an ordering on them, but we can forget about that. So they're parametrizing effective 0 cycles of degree K that are each rationally equivalent to one another. So under such a situation, then the following 2 form restricts to 0 on Z. So I can look at the sum from I equals 1 to K, I can look at the ith projection, and then I can pull back omega. So this is a 2 form on S to the K. It's a holomorphic symplectic form on S to the K, essentially. And I can restrict this 2 form to Z, and I get something which is identically 0. So basically Z is totally isotropic for this 2 form. So this is actually imposing a very interesting condition on what Z can be like, given, of course, if omega is non-zero. If omega is 0, I'm not getting anything interesting, but if omega is non-zero, for instance, this was used by Mumford to prove that the Chow group of 0 cycles of an abelian surface with non-zero geometric genus is gigantic. Okay, so this is the main result that we're going to be needing in the proof of our theorem. So let me sketch the proof for you. So by this theorem of Alzati and Pirola, I know that the degree of irrationality is at least 3, and by this result of Chen, I know that it's at most 4. So what I'm going to show is that if I do have a dominant degree 3 rational map from my abelian surface to P2, then I get this condition on the intersection pairing that I stated before. So suppose that I do have a dominant degree 3 rational map. So I'm going to call it phi. And I'm going to play a little bit. I'm going to resolve the indeterminacy of phi. So I'm going to blow up the indeterminacy locus. So I still have this rational map phi over here. It goes to P2. I get a morphism over here, phi tilde. And I'm going to get U, let U contained in A be an open on which the rational map phi actually restricts to a morphism. So maybe the first observation that I should make is that the fibers of phi, so the fibers of phi, what do they look like? They look like triples of points. But let me draw this schematically what this rational map phi might look like. So I've got my P2 down here. I've got my abelian surface. I'm looking at a rational map phi. And the main observation is if I look at the fibers over two distinct points, the fiber over here is going to be 3 points, the fiber over there is going to be 3 points. Of course, if I take the points downstairs generic. But the point is that these fibers, these effective zero cycles of degree 3, they're going to be rationally equivalent to each other. Why is that? Well, these 2 points downstairs are clearly rationally equivalent to each other because they're 2 points in P2. So I can just draw a line between them. And that gives me kind of a P1 interpolation between these 2 points. And so these effective zero cycles of degree 3 upstairs are going to be rationally equivalent to each other. The 2 zero cycles that are rationally equivalent to each other on an abelian variety, they have the same Abel-Jacobi image. So they sum up to the same thing. So these 3 points here, they're on an abelian, they all lie in the abelian variety A. The 3 points here lie in the abelian variety A. And if I take the sum of these 3 points, I get the same thing as if I take the sum of these 3 points over there. So basically, I can assume that the fibers of phi, so fibers of phi, they all lie on the same fiber of the summation map, but I can actually assume that they lie on the zero fiber of the summation map. Why is that? Well, I could change the origin of my abelian variety, so I could play with that. So fibers of phi all lie in the kernel of the summation map that goes from A3 to A. Okay, so let's see how that is going to be useful for us. So we're going to be considering a cycle that I'm going to call Z. The cycle is going to be the following. I look at pairs of distinct points in U such that phi of A is equal to phi of B. I remind you that U was this open on which phi is actually given by a morphism. So this is going to be a cycle, and I'm going to take its closure. Let's get a cycle in A squared. And so the point is the following. The point is that Z almost parameterizes triples of points that are rationally equivalent to each other. So let's see how this goes. So I can look at the morphism iota. It's going to go from A squared to A cubed, and that's going to send AB to AB minus A minus B. So Z parameterizes pairs of distinct points that map to the same thing. But if I have two distinct points that map to the same thing, I know that the fibers of phi all map to 0. So if I have 2 points in the fiber, I can actually tell you what the third point in the fiber is going to be. If I have a point A and a point B, I know that the third point of the fiber is going to be minus A minus B. So what this means is that if I look at the image of Z under iota, so iota of Z, it's the same thing as triples of points, A, B, C, belonging to U cubed, such that phi of A is equal to phi of B is equal to phi of C, and A is not equal to B is not equal to C, and A is not equal to C. So basically 3 distinct points that all map to the same thing. This is what this parameterizes, and I take the closure of this thing. But clearly this is the same thing as saying that I take the closure of the fibers of phi. And as I said just before, the fibers of phi, they're all rationally equivalent to one another. So iota of Z, so by Mumford, iota of Z has to be totally isotropic for the sum of the pullback of the two forms. So by Mumford's theorem, I know that the sum of the pullback of the two forms from I is equal to 1 up to 3 is going to restrict to 0 on iota of Z. This is for any two-form omega, for any holomorphic two-form omega. So I'm actually going to pick omega such that the integral of omega wedge omega bar on my abelian variety is equal to 1. And I'm going to rephrase this result of Mumford. So I have this statement of total isotropy, and I'm going to rephrase it just in cohomological terms. So another way to write this is that I can look at the cohomology class of Z, and I could cup it with iota star of the sum of the pullbacks of the omega, and this has to be equal to 0. But in particular, this implies a slightly weaker statement, which is actually going to be the one that we're going to be using, since in that case it happens that this weaker statement gives us exactly what we want, and it makes the computation much simpler. So I can pull back this holomorphic form, and again I can wedge with a pullback of the sum of the pullbacks of the anti-holomorphic forms. So this is going to be equal to 0. So this is the statement that I'm going to be using. So I'm going to call this cohomology class eta, and eventually the statement that we get is zeta wedge with eta is equal to 0. So we get some kind of constraint on the cohomology class of Z. So our result is going to pop out from this, along with the fact that we're going to have a simple computation of what the cohomology class of Z actually is. So Z is given in this very nice way, just saying pairs of distinct points in U that map to the same thing, and then take the closure of that. So it's actually quite easy to compute what the cohomology class of Z is. So let me do that right here. So the Z, again, this is pairs of distinct points, AB in U, such that phi of A is equal to phi of B. So how could we do that? Well, we could push forward by the blow up, pi cross pi star, phi tilde cross phi tilde star of the diagonal on P2. So when I pull back the diagonal on P2, what do I get? I get pairs of points that map to the same thing. Of course, I'm going to have extraneous components because I don't want pairs of the same points that map to the same thing. I want pairs of distinct points that map to the same thing. So I'm going to have to remove the diagonal on A tilde to get rid of this extraneous component that comes from the diagonal. So now I'm looking at pairs of distinct points that map to the same thing. But I also have a situation where what could happen is I could have some curves, I could have two curves in A tilde that get contracted under this map. They both get sent to a point. Right? So in this situation, let's say that this is C and this is D. Things in C cross D, the generic point of C cross D is going to consist of is going to be a pair of distinct points that both map to the same thing. So we're going to have extraneous components of the form C cross D that come from contracted curves mapping to the same point. So basically, if I really want to have just the closure, Z was the closure of this locus. If I really just want to have the closure of the pairs of distinct point on U that map to the same thing, I'm going to have to remove some products of curves with some multiplicities. Okay, but the point is that once I actually do this computation, the cohomology class of Z is going to belong to 3 times the class of A cross a point plus point cross A minus the class of the diagonal on A plus something that lies in sim2 of neural severity of A. So we know that Z lies in some affine space in the cohomology, and I know also that Z wedged with eta is equal to 0. And these two ingredients together are going to tell us exactly what we want. So why is that? Well, if I compute 3 A cross point plus point cross A minus the diagonal on A, and I cup that with eta, I get 12. So this is where the 12 comes up in this theorem. So this wedge is equal to 12. Whereas when I wedge with, when I look at what wedging with eta does on sim2 of neural severity of A, this is exactly the same thing. So this is equal, this coincides with the intersection pairing. Sorry, this is not 12, this is minus 12, intersection pairing. So since I know that Z wedge eta has to be equal to 0, I got that Z wedge eta is equal to 0, and this belongs to minus 12 plus something in the image of sim2 of the neural severity, the pairing on neural severity. All right, so this is exactly where I get the statement of the theorem. Okay, so I should say a couple of things. So this answers certainly Yoshihara's first question, which we wrote here. So this is a yes. There are abelian surfaces with degree of irrationality 4. Actually, most abelian surfaces have degree of irrationality 4. And it answers the second question negatively. So the degree of irrationality is not an isogeny invariant. Why is that? Well, if I look at a very general 1-2 polarized abelian surface, I know that it has degree of irrationality 3 because it contains a smooth genus tree curve. So again, by this result of Tokunaga and Yoshihara, it's going to have degree of irrationality 3. But a very general 1-2 polarized abelian surface is going to be isogenous to an abelian surface with a very general abelian surface with a larger polarization, which itself is going to have degree of irrationality 4. So certainly the degree of irrationality of abelian surfaces is not an isogeny invariant. Finally, I should say, if you're interested, this paper about this result is on my website, and you can also find my thesis there where I extend this result from the case of abelian surfaces to the case of abelian varieties of a larger dimension. So what we can say is that if you look at a very general abelian variety that has a sufficiently large degree polarization, then the degree of irrationality of A is greater or equal to twice the dimension of A. So again, there are exceptions, but for most abelian varieties, the degree of irrationality is at least twice the dimension of the abelian variety. So thank you for listening, and I hope you enjoyed.